Okay, in this presentation we're going to look at confidence intervals, and we're going to look at 95% confidence intervals. Not particularly important here, is more what we're interested in is the sample sizes. So let's read the question. Analyst A collects a random sample of 30 claims from a large insurance portfolio and calculates a 95% confidence interval for the mean of the claim sizes in this portfolio. She then collects a different sample of 100 claims. So we have two different cases, the 30 claims case and the 100 claims case, from the same portfolio, and calculates a 95% confidence interval. So explain how the width of these two confidence intervals will differ. We'll sort of deal with that one first off, okay? So what I have here is, with a large sample size, the standard error of the sample mean will be smaller, giving it a narrow confidence interval. I'll go into more detail on that because this is actually very important. So in the first case, what we have is, let's say, X bar 1 and S1, okay? And in the second case, what we have here is X bar 2 and the sample standard deviation 2. What we're sort of saying here really is that they actually should be fairly close together, such that the difference is fairly negligible, okay? So it's not the important difference, okay? That, they should be fairly close estimates according to each other. So that's not important. In both cases, we're also dealing with a 95% confidence interval, so the quantile is the same in both cases. So it's really the standard error is what is of interest here. So the standard error is sigma divided by n, and what we do is we would estimate that by s divided by the square root of n. Now here s is pretty much a value, let's say that pretty much they're both roughly, both sample standard deviations are roughly equal to s, okay? That they essentially do is just use s to sort of signify a rough approximation of the sample variances in both cases, okay? Now, what we, ultimately everything is an estimate of this sigma, okay? So that's really all we're doing with that. Now, so actually that's the key thing there, really. That we're only using the sample standard deviations as an estimate for the sigma, the population standard deviation. Anyway, I digress. This is the important bit here, that the square root of n is part of the denominator. It is the denominator. So what happens is, as the denominator gets larger, this overall figure here gets smaller. Okay, and that's the key thing there. So it gets narrower. So as n goes from 30 to 100, the standard error decreases. Okay, and that means that the interval gets narrower. Okay, so it's less of an interval around the sample mean. Okay, which is essentially what I was getting at there. With a larger sample of 100 claims, the standard error of the sample mean will be smaller. And the reason is that the sample size is part of the denominator of the standard error. And that's the key thing driving that down. Okay? So the second part. What was the second part? Analyst B, so let's go up here, obtains a 95% confidence interval for the mean claim size of this portfolio based on a different claim of 30 claims, different sample of 30 claims. She subsequently realizes that one of the claims in the sample has an extremely large value and will be considered an outlier. She decides to replace this claim with a newly selected one whose size is not an outlier, and a new 95% confidence interval will be obtained. Explain how the two confidence intervals will differ in the case of analyst B. Essentially, what happens is that the replacement of the extreme value will result in a smaller sample size, or sample mean, okay? Which means that the interval will be shifted to the left. So essentially what we're saying here is that X bar will be reduced. What we would expect to happen, it's not as obvious, is that the variance of the sample will be smaller. Essentially, it's got less range. So that should result in a very smaller value for sample variance, okay, and which should end up with a narrower confidence interval. Again, as if S decreases, even though it's really just fairly slight in this instance, one outlier shouldn't make a huge difference, really. It could, but maybe not. But essentially what would happen is that if S decreases, if S squared decreases, that means S decreases, and that means this term also decreases. So that would also narrow it, okay? So that is the effect of an outlier, removing an outlier. The mean would be reduced and the variance would be reduced, which means the sample standard error will be reduced. Okay, that's it.